Okay, am I even sharing my screen? I'm not. Okay, now I'm sharing my screen, right? Maybe? Which screen am I sharing? Do you guys see the Math Learning Center screen?
Yes.
Yes.
Okay, this is going to be an interesting recording. All right, so what does this mean? So y'all broke out into groups and talked about it, so let's see. It means we're not happy. Is that what this is right here, or are we just messing around? Okay, so the model is used to show how addition is being done with the yellow and green blocks. It's a good visual representation using base 10 blocks, and it's a good way to show students how to carry over numbers to other place value. Ooh, man, carrying place value stuff. That is wicked cool. Okay, see what else we got. It means 24 plus 37 is 61 because it is a simple addition problem using blocks to display the problem. Okay, cool. I like that. You're adding the two groups together. Okay, the squares represent the numbers. The squares help us visualize the numbers easier for new learners. Yeah, I like that too. Cool, these are all awesome. Over here, we're using an algorithm, and oh, it looks like you tried to cover up this one with this one. I gotcha, yeah. Okay, so let's just smite that one. Okay, so yeah, so we have a number plus a number equals another number, and I'm glad you wrote that. I want to talk about that kind of notation in a little bit. Cool, so it means addition, right? That's it, and then there's all these little subtle things we can think about in it. So I just want to play around with how this means addition, and ooh, what did I do? Cancel. I hit some weird button on my keyboard because I got excited. All right, so yeah, so what do I see here? So what does this mean to me? So I'm just gonna go back to my original one here. So here I see 10, 20, and 4. So that looks like 24 to me. So I'm gonna write down, do I get to pick another color somehow? Why is this red? Oh, and what does that do versus that? I don't know. Oh, colors. Okay, red looks angry. I don't wanna be angry. So this looks like, or doesn't it work? Oh, is that, what? I broke it? Hello? It worked earlier. Huh. I'm recording this broken stuff. Okay, can I write on somebody else's? I'm gonna write on yours. Will this one let me write on it? Pen, write. No, I broke it somehow. What did I do wrong? Interesting. What if I try to use my mouse to write? Oh, I can use my mouse, but not my magic pen? Well, that's not fair. Okay, fine. All right, let's, ooh, whoa, sorry, I'm having all kinds of technical issues today. Bear with me. Let's try this one more time. Green, no, blue. So this right here is 24. Come on, Gary, get it together. Oh, what? Okay, there we go. This right here, what, 10, 20, 30, 5, 6, 7. So that one is 37. So it looks like I'm trying to show 24 plus 37. And what do we get over here? We get 10, 20, 30, 40, 50. And then over here we have what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it looks like I get 50 and 11. So I traded one addition problem for another. Huh. Okay, it's a good visualization though. Oh wait, I know. 11, that's really a 10 and a 1, right? So I could turn off the pen and then let's see, I could just circle some of these and say stick them together. Oh, look at that. Now I see 61. I think the pen's gonna work. Ah, there we go. Okay, so we gotta remember, we know a lot more than kids, and to some kids, they're just gonna look at that other blob and say, yeah, that's 10, 20, 30, 40, 50, and here's another 60 over there, 1. Right? Some kids are just going to see that this group, right? Oh, now it works. This group right here is another 10. So there's my 60 and this 1 right there. Other kids are pretty literal about what they see, and they're going to put them together, and they're just going to see it, let's see, this one, as 50 and 11. Okay. Now, to complicate matters here, I'm going to switch to my other whiteboard. The picture of this. Let's get that scribbling out to there so I can write with my better pen. Maybe, can I get it to work? Why? Oh, all right. Someday I'll get this figured out. Maybe. Try again, Gary. There we go. Okay, now I can actually write on it with a real pen. So to complicate matters is the way we write things. Like sometimes we write 24 plus 36, or no, 37, I lied, equals, and then we come up with an answer. Other times we write it different, right? We stack it, 24 plus 37. And you'll see it written different ways when kids get to this. Now, so they have done a lot of work with addition of single-digit numbers before they get to the 2-digit numbers and higher. So this is a more advanced addition problem for kids in the early elementary school grades. And this notation right here is going to be challenging for a lot of kids because of the separation. You know, you have the 10s, 2 10s way over here, you have the 3 10s there, you have the 7 1s there and the 4 1s there. We teach this method about stacking and carrying. And a lot of kids struggle with it at first because they're used to doing things like 4 plus 7. They've done this 1,000 times before they see that. 4 plus 7, either they count up on their fingers or they just remember, oh yeah, that's 11, right? And then all of a sudden they get over here and they're gonna wanna write the 11 like that. Okay, but that's not what we train them to do. There's a whole lot that goes on from here to here in terms of that transition. It's not a thing that happens overnight. Okay, a lot is going on. But some kids get that transition very well. Other kids struggle along that road mightily, and they're going to get to this point, and they're going to write 4 plus 7 is 11. I'm going to throw it down there like that. Okay. Now, if they have a good idea about place value because they played a lot with blocks like this, and they view this as 2 10s and 4 1s, then they might also look at this and say, hey, you know, this is a 2 10s plus 3 10s. Well, that's 5 10s or 50. Oh, well then, yeah, we just have a 1 and there's 6 10s, and oh, okay, it's 61. So this is kind of a natural way to go about it. And you might look at that and say, that ain't natural. So I'm just kind of curious. I'm gonna switch to my grid view here. If you could share with me whether you think that was unnatural. Whoa, that was weird. Try that again. Like, is that unnatural? Show me a thumbs up or wave or something. You guys still out there? Anybody there? Oh, there we go. Thank you, Lauren. That's kind of weird. How many people think this is not weird? This is like, no, I get that. That's cool. I've seen that before. Anyone seen this before for addition? No reaction. Oh, there's Amy. Amy says, no, not seen that before. Oh, I got some chats. Let's check out the chat. Julian's done this before. Okay. So we have quite a variety of responses to this. All right. So the base 10 blocks are kind of a literal thing. and it's a good thing for kids to have this literal representation because most kids aren't very abstract. There's a few kids who are. They can pick up these abstractions, these models. But a lot of kids, that their brain just hasn't got those processes down yet, the idea of the layers of complexity of reality. And so seeing a group of 10 here is natural for some kids and not for others. And we actually have to, sit down with those kids and pick blocks up and play with them. So for this one right here, let's turn off the pen, maybe. Come on, pen. There we go. We might actually pick these guys up and try and build a 10 out of them, just to reinforce that that group right there is the same as this group over here. And so then I can circle that and tell the computer to stick them together for me. Now, drawing with a mouse like this is kind of a pain in the butt, but now I have a single 10 that I can treat like a single 10. Okay, and then there's the one over there. So this idea of physically trading in, I think, is really important for a lot of kids. So I just want to make a note of that over here. Like this step to this step, I'm thinking about physically trading in. Ten ones for 110. And a lot of kids need that physicality to better grasp the abstraction we're trying to do here. Because really numbers are very abstract. The idea of 24 things, this set of symbols right here, is any 24 things out there in the world. That's a big deal. There's a lot of groups of 24 things out there that are possible. So kids getting to this point, they've come a long way in their level of abstraction, but they still have a ways to go. So what we're going to play with today are the idea of modeling whole number addition, the idea of how we go about processing whole number addition, and then some rules that come along with that. So on this screen here, I think I'll just redraw this on a new page. Two big ideas. First one for today is models for whole number addition. And a model is when we model, right? We get physical. Okay? We actually have some physical objects that we play with. So the model would be like saying, there's 10, there's 20, 1, 2, 3, 4. So this is a model for 24. What it means to then model addition is another idea, which we've scratched the surface of, and we'll dig into it a little more in a minute. The other thing we have to deal with are the processes for making addition happen, and those are called algorithms. So examples of algorithms are if somebody says, please add 24 to 37, I might stack them like this and then say, let's see, 4 plus 7 is 11, write the 1 for the 10 up there and the 1, 1 down there. And then 2 plus 3 plus 1 is 6, so my answer is 61, okay? So that's an algorithm right there, right? There's nothing physical about it. I don't have blocks to play with. I don't have toys. I'm not showing you something physical. I'm just scratching these symbols on a piece of paper. This is an algorithm. An algorithm is a process that we follow to get the job done. I just presented a different algorithm a minute ago. I took 24 plus 37 and I added it in a very different way. I said 4 plus 7 is 11. 20 plus 30 is 50, and then I combined the 11 and the 50 to get 61. Okay, so that's a different algorithm than this one. I think most people grew up doing the green and red algorithm, but some people might have grown up seeing the blue algorithm here. So we're going to give this green and red one a name. We're going to call it the standard algorithm because this is what's most standard in the US. Standard algorithm. This one right here is often referred to as an expanded algorithm. So if I say, hey, show me the expanded algorithm for addition, it means do this. And we'll talk more about that. Okay, so we'll come back to algorithms. We're going to play with models for a little bit. And then we have a third thing to do, which are rules and properties of addition. And then we'll repeat all this probably next class for subtraction. All right, so back to models, and then algorithms, and then rules and properties. So a model is where we get physical. We want to physically show what is happening. Now, in order to do that, we have to be able to do two things. We've got to show what is a whole number, and we have to show what is addition. Okay, so we got some preliminaries. So first, what is a whole number physically? And we have many options for what is a whole number. I chose in the beginning to use base 10 blocks. So one option out of many, base 10 blocks. And usually I'm in the classroom with you and I have this big box of these toys that look like those things up there, but they're 3D things. And we have to settle for these digital ones. Oh well. There's lots of things that you could play with. In the early days before these things were like mass marketed, these toys for teaching, teachers would make their own. So another option that I used to see when we had smaller budgets and this stuff wasn't out there, it could be like beans to represent ones, and then popsicle sticks to represent tens. And teachers even have the kids make them, like glue 10 beans to a popsicle stick to show 10. And each kid would have their own set of popsicle stick beans, and they can paint them and have fun. So it could be like an art project too, arts and crafts and math. So both of these types of toy to get physical, these would be related to a way of doing addition. So this is the second thing here. What does addition mean? So that's what we got to come up with next. So we have what is something physically, what is a whole number, and then what does addition mean? And we put the two of them together to create a model for addition. So that's the next question. So you guys shared with me your thoughts on this diagram. Okay, so this is a representation. We were modeling addition, and everybody looked at this and saw the same thing. This is a model of addition, and you all talked about it in slightly different ways, but everybody here saw a model for addition. So based on this model, based on the addition of those two numbers we just did, what does addition mean? How do I explain it without showing it? Or how do I explain it so I can show it? What does it mean to add? I can't say it means to add because that's using the word in the definition. So I need some other words for this. Help me out. What does addition mean?
It's the combination of two different items.
Combination of two different items. Okay, I'm with you there. combination of two different, and you seemed a little uncertain about the word items. So I'm gonna put that in quotes, question mark. Okay, anybody else want to take a stab? Oh, I got some things here. Okay, bringing subjects together, Avali writes, and Amanda writes to put together. Okay, so bringing subjects together. And then to put together, so that's very similar. Okay, yeah, so thinking about that picture we had earlier, this right here, get the pen back, come on, darn it. All my different programs are conflicting with each other. So that's it, no, it doesn't work with that pen. Yeah, so it means take this right here and put it together with that right there, right? So put together, combine. So we have a couple different words that are nice. Let's get back here. So I'm just going to highlight some important words here. Combination, combine, bring together, put together. Okay, so that's kind of like my first version. Let's see, is that back here? No, back here, yeah, okay. So somebody gave me this group of subjects, items here, and somebody else gave me this green group of items or subjects, things, whatever you want to call them. And I put them together right here, okay? So somebody says, hey, add those, add means put together. And I say, okay, here you go. They're put together. I go home now, I'm done. Am I done? I took that group, I put it together with that group. Okay, so it means a little more than just combination or put together. So how do we go one step further with what this means here? Because I put them together there, but I don't really have an answer yet. Total, yeah, I got to come up with the total. Okay, solve, yeah. And more specifically, I got to count, right? I got to say, how many are there now? 10, 20, 30, 40, 50, over here is 61. I count 61, okay? And whether you count it by looking at them, or you come over here and count 4 plus 7 is 11, then 20 and 30 is 50, 50 and 11 is 61, right? I'm counting here, I'm counting there. So, okay, now we got it. We got to put them together and count it. Just putting together isn't enough, because then we get weird answers like 50 and 11, or here's my answer right there. So all of these are right. That's right, that's right, that's right, but they're only half the truth. We have to do whatever that says and count. And that count that we end up with is called a sum or a total. Okay? So we could say we total it, we could say we sum it, we could say we count it, right? Somehow I have to reconcile what it is in one shot. Okay, so I'm going to tidy this up a little bit, and then we're going to do it a couple more times, look at the activity, and show another method. So what we just put together is called the set model for addition of whole numbers. In the set model, addition means to combine and count. Now, I like using base 10 blocks because I can use them to show kids why we carry. We have that crazy carrying thing we do. Okay, why do we do that? And then, but we could use anything. We could use pennies and dimes. We could use beans and sticks, right? There's lots of ways to do it. But the bottom line is, in the set model of whole numbers, addition means to combine and count. Okay? We could say put together and count. That's just as good. Like some kids, I might say the word combine. They're like, my mom never used that word. What the heck are you talking about, Parker? Okay. So again, we have to have different vocabulary because not all of us have the same, set of words and definitions in our heads. But combine, that's a good one. Put together is another great one. And so just real simple, at first we're going to do things like, Gary has 5 green apples and Julia has 4 green apples. How many do they have together? And so we put them together into one new set, and this is our sum. Okay, so this shows that 5 plus 4 is 9. Okay, so that's how we start off real basic. So this is like first grade, maybe even kindergarten kids are doing this already. They know how to put stuff together. They know how to count. They know how to add. We just got to train them to do bigger numbers. And that's where the base 10 blocks come in. So sometimes with base 10 blocks, we have to do a little bit of extra work. So let's take a look at the previous problem I had and show 24 plus 37. So I need some base 10 blocks. I'm just going to draw them in here as opposed to go to that app. So here is my best drawing of 24. And then here's my 37, to the best of my artistic ability. Sorry, my pad is sliding around the table. It's sitting on my notebook. Let's get neater here. That's a little better. So draw your best 37. And I like groups of 5 whenever possible. So often I'll write something bigger than 5, but smaller than 10 like this as a group of 5 and 2 ones. Because a lot of people can look at that and see 5 and 2 is 7. But if I have them in one long string, they're going to be like, is that 6, 7, or 8? So this just helps visually recognize it. So then I'm going to make a note to myself that I'm going to combine these. Combine has a B, not a P. And when I combine them, right, I'm going to regroup some of these. So I'm going to take these guys here, and let's see, this guy here and that guy here, and I'm going to trade 10 ones for 1 10. And that's going to give me my new group, right? So now I have 1, 2 from the first set, 1, 2, 3 from the second set. And then I have my new group I just traded in. And then I have 1 left over. So the answer must be 61 because of that trade there. And eventually we're going to connect this to an algorithm. So let's do the connection to an algorithm. So the stuff I did in blue and green, that's a model. I'm just saying addition means to combine and count, but I got to do a little trading in. Sometimes the counting is a little complicated. Connect to an algorithm like our standard one, 24 plus 37. Oops. 4 plus 7 is 11, but I carry that 10 up there and leave the 1 behind, and then 10, 20, 30, 40, 50, there's my 60 right there, 61. And the connection between these two is this carry here is the trade from above, from the model. Why do we carry? This is why we carry. Because we found a group of 10 that needs to jump to the next group. One group of 10. It jumps to the next column, the next place value there. Okay. Similarly, this comes up if I use the expanded algorithm. So alternatively, The expanded algorithm for 24 plus 37 would be to just say 4 plus 7 is 11. I have 11 ones in this picture. And then 20 plus 30 is 50. And there's my 61. And so in this case, this extra number here is the trade from above. That 1 jumped into the next column magically because of the way we write numbers. So this is nice. It uses a little less space. The standard algorithm uses a little less space than the expanded algorithm. Remember, this is what's called the expanded algorithm for addition. So again, algorithm is a process. There's nothing really physical about this. I'm not showing you blocks. I'm not showing you beans or pennies or dimes. I'm just saying, hey, do this because it works. Do this because it works. That's how you get the answer. You don't got to draw pictures. At first, the pictures are nice to get this connection about how things are working. And I don't know about you, but a lot of times when I do math, I see pictures of math and numbers in my head. Like when I see 7 and 8, I can see them regrouping into 15 when I put them together. Okay, the way they trade off with each other to make that happen. Sometimes when I think about 6 and 5, I think about a dice and how that's going to give me 11. The way those dots form on the dice. We all have these physical models that we've developed over time, and so this is just a slightly different one. So this picture right here is again set model for addition. And it's where I use physical objects to show how to combine and count. And sometimes it's complicated because I have to trade in, and other times it's super simple. Take 5 things plus 4 things, you get 9 things. Why is 5 plus 4 9? Well, count. When I come over here and count, I get 1, 2, 3, 4, 5, 6, 7, 8, 9 things. Oh yeah, 5 plus 4 is 9. Why? Because we counted 9. Simple as that. So a model is where you get physical with an explanation. An algorithm is where you just write down some symbols, some numerals, and you get it done based on some process. Okay? So 2 different things. Models are necessary to help people understand why is 4 plus 5, 9? Why is 24 plus 37, 61? On the other hand, once I start getting into bigger numbers, like suppose I have to add 376 to 588. I don't want to draw a picture of that. I just want to get it done, okay? And so I could get this done by stacking, or I could get this done with the expanded algorithm. So just for fun, write down these 2 numbers and come up with the sum. And then I'm going to show you a few different algorithms for this, and then we'll look at a different model. So I'm assuming most of you wrote down what we call the standard or regrouping algorithm, is where we write one number right underneath the other one, lining up place values. And then we do our regrouping or carrying. And that is 6 and 8 is 14. And instead of saying it's 14 ones, we say that 14 is 1 10 and 4 ones. And then 7 and 8 is 15 plus 1 is 16. And we carry. And 5 and 3 and 1 is 9 on a good day. So that's the standard algorithm. Sometimes it's called the regrouping algorithm because we are regrouping a bunch of ones as a 10 and some ones. Okay. Then there's what I referred to as the expanded algorithm. So let's try that here. An expanded algorithm just depends on place value. And so we're just going to take that same problem and write this down with me, give it a shot. So I'm going to expect you to learn some other algorithms. I'm going to present quite a bit. You don't have to learn them all, but you're going to learn some. And I'm going to use a different color to kind of illustrate what's going on. We don't do any carrying with this one. We just say, let's see, 6 plus 8 is 14. And we just write it down. And then we have to realize that that's just not a 7 and 8, that's a 70 and an 80. And 70 and 80 is 150. So we got some, that's a lousy looking 5. Let's try that again. That's a little better. And then moving over to the next column, that's not just a 5 and a 3, it's a 500 and a 300. 500 and 300 is 800. And then we reconcile what's left. And so we have 4, 5 and 1 is 6, 8 and 1 is 9. We get the same answer as before, it just looks a little bit different. Are the zeros necessary? I would say they are, because we're emphasizing the place value. Don't leave them blank. Otherwise, it's easy to lose track of stuff. So that's the expanded addition. Nothing gets carried, everything comes down below. And then we kind of, instead of doing the carrying as we go, we just do that at the end. So at the end, we take the 1 and the 5 to get the 6, the 1 and the 8 to get the 9. And it's a nice way, some kids like it. This is taught in a lot of other countries instead of this way. And sometimes it's taught in this country as just an alternative. And that alternative could be to help kids that were, they were already doing good and now they're going to get a little better, or kids that were struggling might do this method better than that one. This is one of my favorite ones. This is called the lattice method, the lattice algorithm for addition. And we pretty much start the same way. We write 376. Straight underneath, we write 588. But then underneath here, we draw a rectangle. That rectangle then gets split into columns for each place value. And then starting in the upper right, we draw diagonals through each one. And that direction matters. So then 8 plus 6 is 14. And so the 14 gets written like that. 7 plus 8 is 15. So the 15 gets written like that. So we have our place for our 1s and our 10s. And then 3 plus 5 is 8. So the 8 just goes here. Now, the next thing I want you to notice here is that there are diagonals being formed here. And what happens if we follow those diagonals? Well, the only thing in that diagonal is a 4. There's a 1 and a 5 in this diagonal, so that makes 6. There's a 1 and an 8 in that diagonal, so that makes a 9. Isn't that cute? Come on, that's cute. Somebody give me a thumbs up or a smile if they think that's cute. I think it's cute. Oh yeah, cool, thank you. I didn't make it up. And this is taught in some South American countries and I think some places in Europe, called the lattice algorithm. All right, now, the letters that I use like R, E, G, and the 3 and the 7, there's a lot of countries that don't use the same alphabet and numeral system we do. There are many other alphabets actively used in the world. Not only that, there's some places where instead of reading right to left, no, I say, which way do we read? We read left to right. They read right to left. They read the other way. So I'm going to present an algorithm related to one of those countries that reads the other direction. This is often called the Hindu algorithm. And I'll do this in a couple of different ways. This freaks a lot of people out, but you get used to it. So instead of starting at the 1s and working your way to the higher places, you start in the higher places. And there's a few different versions of it. I'm just going to go over the standard one. 300 and 500 is 800. So I'm just going to put an 8 there. It's in the hundreds column, so it's got to be 800. And then I move over to the next place. 70 and 80 is 150. I mean, you could look at that and say 7 and 8 is 15, and I'm sure lots of people do. But then I have to note that the 5 goes here, and the 1 has to jump over here, making that 8 a 9. And I'll repeat this again. It takes some getting used to. And then 6 and 8 is 14. The 4 1s go over here. The 1 jumps over here to the 5, making it a 6. And so there's my answer, 964. And that's what's referred to as the Hindu algorithm. It goes left to right. Which I think is also pretty cute. Wow, I never thought of that. Look at that, that's awesome. So there are a lot of ways to add. People around the world don't all do it this way over here. Although this is standard in the US, it's not standard everywhere else. Some places the expanded algorithm is more standard. Some places it's the lattice algorithm. Some places it's the Hindu algorithm. Cool stuff, eh? Okay,
so ultimately though, it's gonna be whatever's easier for whatever child's brain is going to be able to process it. Right?
Yeah, and then as far as that goes, like when I've only volunteered in elementary schools. I haven't taught there. I only taught high school and middle school before college. But every room, the abilities around you are so diverse, right? Some kids are just flying ahead and you can't keep up with them. Other kids are so far behind, you're trying to, how do I catch this kid up, right? So there's all these different strategies. And the main reason I'm teaching these other algorithms to you is I'm just trying to get you to realize, although we know so much that we take for granted about the things that we do, there's so much that we don't know. And I'm just trying to put your brain in the point where, man, I don't know how to do this. How did he do that again? Why did he put that 1 up there? Right? And there's lots of kids for weeks who are going to go on, why did I put that 1 up there again? Why can't I put it down here? Right? So there's 3 reasons really I'm going over these algorithms. 1, I'm trying to challenge you to help you rethink what you thought you know. 2, there's going to be kids that struggle with this algorithm here, the standard way, and maybe the expanded might help them catch on better. Or maybe they're going to think the lattice is so damn cute, they're just going to love it and do it, right? And then there's the kids who you can't keep up with and you just got to give them something to do, right? So you show those kids that are done with the homework and causing trouble, hey, do this for a little while. See if you can do it backwards, right? Get the right answer. So you can use this for the challenge, the students that need a challenge. You can do this for the kids that are struggling and need more help. But I wouldn't on your own decide, I'm going to teach all my kids the lattice algorithm in my classroom, because you got to make sure you're using a similar curriculum to the other teachers around you. But it could be you're going to use this as a supplement. And teachers supplement all over the place because every kid's need is different. All right, let's see. Let's back up a second to look at models again. So we did what was called the set model. Another model for addition is the number line model. And anytime we have a model, we got to state, okay, what is a number in this model and what does it mean to add in this model? So number line model for addition, and I guess I should be more specific, of whole numbers, although it really works for any kinds of numbers, but best for whole numbers. So a number is a distance on a number line or a position on a number line, is the premise here. And then addition just means to continue to count on the number line. There's a couple of versions of this. So for example, if I wanted to show 5 plus 4 like I had earlier, I first need a number line. And then that number line needs numbers. And often kids are going to have a ruler taped to their desk or a ruler nearby, and that's going to be their number line. And having graph paper, having that actual number line is super useful for a lot of kids because some people are messier than others. So just example of that, let's get rid of this background here. A lot of kids and adults I know, if I ask them to draw a number line, their penmanship and accuracy is a little questionable, and their number line might look something like this. Right? That's not a good number line because the numbers aren't all the same distance apart. So a number line should be like a ruler. Okay, so this is not a good ruler. So to kind of balance the abilities different people have, let's give them some equity and say, hey, here's your number line. So give them graph paper, give them a pre-made number line, give them a worksheet with number lines on it. Because otherwise you're going to get all kinds of weird stuff. And so what I do is on this, it just means to count on. So, I get my 5, that part's pretty easy. I can just go, oh, 5 is right there. And then for 4, I just count on 1, 2, 3, 4. Oh, I mislabeled my number line, didn't I? See what I mean? Not all people are created equal. We make mistakes. 9, 10. Yeah, thank you, Emily. That was pretty funny. I really embarrassed myself in my previous class. I did something stupid. What was it? Oh, I thought I had shared the screen and I didn't. And 5 minutes went by before somebody finally said something. We can't see what you're writing, Parker. It's like, man, I was so embarrassed. Okay, anyway. So I count up from 5, my additional 4, and then there's my 9. So 5 plus 4 has to be 9. Sometimes this is taught a little bit different with arrows instead. So there's kind of a, it's really the same thing, but we could do it with arrows. And so the only difference with, arrows is I just draw an arrow starting at 0 that is exactly 5 long. And then I start right at the end of 5 and I draw an arrow that's exactly 4 long. And then I just want to double check that that really is 5 long. Yep. And that this one really is 4 long. Yep. So the answer has to be 9 right there. So we just place arrows. Back to front, starting at 0. In some books, or if you look this up, you might see it online and in other places. Sometimes those arrows are also known as vectors, so AKA vectors. So this is sometimes called the arrow model for addition, or the number line model for addition, or sometimes even the vector model for addition. I just like calling it the number line model. But this is different than a base 10 block, right? I'm just hopping around on a number line. And sometimes the kids are given little tokens to hop around on the number line and move around. And those tokens might be an action figure or a car or just a chip or a penny or a nickel or a quarter or something like that to keep track of where they are and move it around as they go. So this is different than the model of the sets, because the sets is a group of things, like a group of fingers or a group of blocks or a group of coins. And in this case, I'm just saying, no, a number, I'm not looking at a number as a group of things. I'm looking at it as like some inches or a measurement, or I'm just counting along there. So it's kind of different physically. So it's treated as a different model. So again, a model is where you physically do something to show somebody why 5 plus 4 is 9. An algorithm is where you have this process that you follow and out pops an answer. Okay. All right. So I'm going to pause there.